Here are some quick notes on cross-sections to accompany Chapter 5 of To Build a Star. So here we're talking about nuclear reaction cross-sections. So I'm going to focus here on the geometric cross-section. So in the book, the sort of physical cross-sections mentioned pi times the radius of the nucleus squared, and it's mentioned that that's often way too big, which is true for astrophysics. But I do want to mention how the geometric cross-section isn't totally unreasonable. So that's pretty much the whole point of these quick notes here. And we'll also mention some other details of cross-sections that are interesting to know. So let's consider a sort of grazing collision here. So we have a target nucleus. In this picture, it's kind of big. It has radius capital R. We have a projectile nucleus. It's smaller in this picture here, has radius R prime. And then the distance between the center of these two nuclei is the impact parameter b. And in this collision, there's a relative orbital angular momentum. Classically, that's this position crossed with the momentum. Because of the angles here, that is the momentum times the impact parameter. And because this is quantum mechanics, we quantize the angular momentum in units of h bar. And our particle is a wave, so the momentum we write in terms of the de Broglie wavelength. We do some algebra here, and we see then that the impact parameter is the orbital angular momentum divided by 2 pi times the de Broglie wavelength. And if you're at a given slice of impact parameter, that's going to correspond to a given orbital angular momentum. So for instance, if your projectile is at this sort of impact parameter slice, because we have to discretize things, in this picture that corresponds to a couple units of orbital angular momentum, okay, times h bar. And so for each orbital angular momentum in this semi-classical picture, you can kind of just consider it as a little bit of a slice of the impact parameter here. And so then if we just calculate the geometric cross-section, because this is a semi-classical picture, then for a single orbital angular momentum, it's the cross-section for this impact parameter slice. We need to take the difference between the area of the circle at radius b plus db, so the impact parameter plus some little slice, minus the area of our circle at the impact parameter minus some slice. So we're just taking basically the area of an annulus is what we're calculating, and we then relate this to our orbital angular momenta, because remember the impact parameter at some slice corresponds to a given orbital angular momentum, and here we're going an inner orbital angular momentum and one just beyond that, so we're going to call that L, and this is L plus 1. And we're using the math up above to do this conversion here, introducing in the de Broglie wavelength times the orbital angular momentum in place for the impact parameter. So that's the swap that's gone on here, and you can do this arithmetic, and you see that for a given slice, a given orbital angular momentum, you have pi times the reduced de Broglie wavelength squared times 2L plus 1, where L is your orbital angular momentum. So then for the total, we have to sum over all orbital angular momenta that are participating in a collision. And so each of these have some cross-section contribution, and we're going to sum over all of those. Now, this is semi-classical, so now we're going to fudge in some more quantum mechanics. What we need to keep in mind is that there is a probability of tunneling through our barrier at any given orbital angular momentum, and that is parameterized in quantum mechanics as a transmission coefficient. And so we're just going to add in a factor here of the transmission coefficient. This is anywhere from 0, meaning you just don't tunnel at all, up to 1, meaning you tunnel 100% of the time. Okay. So then for the example here, let's just take one limit. So if you're at relatively high energy, then we can approximate the transmission coefficient is 1 for all orbital angular momentum up to some maximum that we'll discuss in just a second, and is 0 for all higher orbital angular momenta. And this is something called the sharp cutoff limit. Okay, and it may seem a bit crude, but we'll see it's actually not too bad for some cases. So, what's the maximum orbital angular momentum you sum up to here? Well, we say that the maximum is when you have this sort of minimally grazing collision. So your impact parameter is just these two circles, the projectile and the target are just barely touching. And so if this is our impact parameter at the maximum, we plug that into this equation, and we can then solve for the maximum orbital angular momentum. And it's given here, right? 2 pi times the sum of the radii divided by the de Broglie wavelength. Now, we're only summing up to some L max. You can see later that if you sum excuse me, over all integers from 0 up to some number of 2L plus 1, that sum is approximately equal to the maximum that you sum up to squared. So then our total cross-section in this geometric picture is going to be pi times the reduced de Broglie wavelength squared times the maximum orbital angular momentum squared, where you solve the maximum based on the sum of the radii of the 2 nuclei that are interacting and the de Broglie wavelength that describes the collision. So this is just the energy-dependent part. Okay, so let's confront this with data. Let's consider the example of carbon-12 fusion. So if we take an energy from 1 to 100 MeV, that's going to change your de Broglie wavelength, but it's also going to change your maximum orbital angular momentum, and you see your answer's around 1 barn. So remember that 100 femtometers squared is a barn. So that's the answer that you're going to get. Now, what energy do we actually care about for astrophysics? Let's calculate that, because then we want to figure out what the actual measured cross-section is so we can compare it to our data here. So if you want to figure out the energy of interest, then as you saw in the book, for charged particles reacting, you have basically that you create this Gamow window, right? So it's essentially folding together the probability of having a given kinetic energy from the Maxwell-Boltzmann distribution and the probability of being able to go through the Coulomb barrier is more or less what you're folding together. And you then do an expansion, you approximate this as a Gaussian, you do a lot of other simplifications, and you get basically that the peak of this Gaussian energy window that you care about is a so-called Gamow window. And in sort of somewhat easy to remember nuclear physics units, you can use this equation here. So you have 0.122 times a quantity raised to the 1/3. And in here we take the charge of one of the nuclei that's interacting squared times the nuclear charge of the other one squared, so it's number of protons. This is the reduced mass that we calculate. And then we have the temperature in gigakelvin, that's what T9 is, squared. So if you plug in your numbers here, then this will give you the energy in MeV for the center of mass at a given temperature. That is likely most important. It's not exactly true because you're making this Gaussian approximation. You're making a very specific assumption about the shape of the cross-section. And so as you get to higher temperatures, environment temperatures, this isn't quite true. If you have a non-smooth cross-section, so like resonances that we'll talk about in a moment, then this isn't quite true. But to first order, this gives you a good estimate for what energy range you care about. Okay. So let's take the highest temperature astrophysical environment that I'm aware of where we care about carbon-12 fusion. So it's explosive carbon burning. It's about 2 gigakelvin. You can plug in your numbers and you get that the center of mass energy is about 3.8 MeV. We want to confront this with data, so we have to convert to the lab frame. So the lab beam energy, basically, so if I have a carbon-12 beam and a carbon-12 target, the carbon-12 beam energy that corresponds to that center of mass energy that we calculated is just the center of mass energy times the mass of the beam plus the mass of the target divided by the mass of the target. And we see that's about 7.6 MeV. So now let's go ahead and look at data. This is the carbon-12 fusion cross-section from the X4 database in the National Nuclear Data Center website. And they have a nice plot feature. So we have the cross-section and barns versus the energy of our carbon beam. And we see that if we look at this energy range that we care about 7 MeV, you have something on the order of 10 to the minus 5 barns. Okay, so quite a bit less than the geometric cross-section. So the book did not lie to you that the geometric cross-section isn't particularly useful for our astrophysical scenarios. However, what I want to point out is that this cross-section saturates as you get to higher energies, And you see, once you're at 50 MeV or so, you saturate right at a barn, as promised. That's kind of cool. So now let's consider a neutron capture cross-section. So something like you'd have, for instance, in the slow neutron capture process in asymptotic giant branch stars. Let's consider fusing a neutron with gold 197. So we can go through the geometric calculation on the slide before, and we'll find that if you have 10 MeV energy, then your geometric cross-section is about 2 barns. Okay. If we want to figure out what astrophysical energy we want to compare to, what sort of astrophysical environment, for neutrons, this Gamow window doesn't make any sense, right? This assumed that you're tunneling through a Coulomb barrier. That's the penalty for being at lower energies, right? But for neutrons, there's no Coulomb barrier. So instead, your characteristic energy that you care about is just and basically the environment temperature. So Boltzmann constant times T. In units that are easy to remember for at least me, you take the temperature in gigakelvin, that's T9, you divide by 11.6045, and that gives you the energy in MeV in the center of mass frame. So we can plug in an astrophysically relevant temperature. So if you take the temperature of the S process, there's actually a couple of environments that it can happen in, but a typical temperature is something like 25 keV. And then let's go again to the X4 database and NNDC website, cross-section in barns versus the incident energy. And if we go to 25 keV, then we get it's about 13 barns. So this time we're quite a bit bigger than the geometric cross-section, right? But as you go to higher energies, what do you see? You converge down to this, single barn, two barn region. So you converge to that geometric cross-section. There's a couple more things I want to say about this plot here. That's interesting. So you see, for the charged particle cross-section, right? This is a log scale. The shape that you're looking at here, this is pretty much mostly responsible, mostly from the Coulomb barrier. So you're basically looking at how the probability of tunneling through a Coulomb barrier. That's why it falls off exponentially like that. But for neutrons, as you go to lower energy, you have this interesting shape. And we can understand that in a semi-quantitative way. So for neutrons, your transmission coefficient, when you're at low energy, is proportional to the square root of the energy. Okay? If you're at 0 orbital angular momentum, and it's 0 otherwise. Okay, so, and this basically just has to do with how long the neutron's kind of dwelling near the nucleus in some sense. So then our total cross-section, we just have one angular momentum that we're summing over. We're going to take that transmission coefficient as the square root of the energy, and we're just doing proportionalities here, because obviously this isn't, this isn't a unitless thing. So then the de Broglie wavelength, right, that has 1 over square root of energy. We square that, multiply that by the square root of energy, and you find that your cross-section goes as 1 over square root of energy, or 1 over v. It's sort of the famous 1 over v dependence of neutron capture cross-sections, and that is why you get this linear slope on a log scale, is because it's a power law. Okay, so that's one interesting thing, and then one final thing I want to note here is that in this one there's some far deviations from the smooth dependence, right? You have these huge bumps here, and these are called resonances. So what's happening is at this specific energy, when the neutron and the gold 197 fuse together, this energy happens to match up exactly to an excited state in the so-called compound nucleus, the neutron plus gold 197. So you match pretty much exactly with that excited state, and so that is called a resonance, because the basically your structure is almost exactly what it needs to be to create that excited state, is like a hand-wavy way to think about it. So at low energies, you're just not seeing any excited states at all. There's no excited states that you run into, and then you start to run into them, and you see these resonances, and then there are so many excited states that it kind of smooths together, right? So instead of having a bunch of peaks, they kind of smooth together, and that's why it becomes smooth again. And so putting this all together, this is basically a semi-quantitative picture of the cross-section versus your interaction energy. In a log scale on the bottom, you see for charged particles, you exponentially fall off at low energies, and then you approach the geometric cross-section. For neutrons, you have a 1 over v, or 1 over square root of energy dependence of the cross-section. You come from above, you're much higher than the geometric cross-section, and then finally you come down to approach the geometric cross-section. And then on top of this hand-wavy structure that we talked about, you have all these sharp bumps, these resonances. And so experimentally, what do we do in nuclear astrophysics? Well, first off, from a theory standpoint, we can calculate, the smooth behavior. We can calculate where some of these bumps are, and then you integrate over this to get a reaction rate, as you'll learn about soon. And so you can calculate this theoretically. Experimentally, what do? We try to measure the smooth dependence where we can, and we try to measure the strengths of these resonances where we can. And then inevitably, we can't measure as low as we want to go, oftentimes for charged particle reactions, or it's rare that we can. And so what's done is we divide out the trivial energy dependence from the Coulomb barrier, and what you get is then the S factor, as that's mentioned in the book. And the S factor is relatively constant, and so then you can extrapolate much more reliably to lower energies. All right, and that is it for these quick notes on cross sections.